In this video, we'll be looking at how the periodic table is organized, as well as nomenclature, which is how we name and write formulas for chemical compounds. Here we're looking at the periodic table, and we want to talk a little bit about the organization of the periodic table. There's a couple different ways we can organize things. The first way we want to organize things are based upon what type of element we're dealing with. And there's three main types. Metals shown in blue on the periodic table, metalloids shown in the orange, and then the nonmetals shown in green on this periodic table. And right away you can get a real quick idea of where each of these are located. Metals comprise the biggest portion of the periodic table, kind of the entire middle and left-hand side. Nonmetals in this upper right-hand corner of the periodic table, with the exception of hydrogens. Hydrogen's kind of the oddball in here. But then the metalloids that kind of straddle in between the metals and the nonmetals. So now that we kind of see where each of these types of elements are located on the periodic table, let's talk about some of the properties these have. So first, our metals. As we said before, we usually see the metals on the middle and the left on the periodic table. Often these are solids at room temperature. Usually when we think about a metal, we think about it being a solid. Generally, these are shiny in appearance, especially when new and fresh, before they've got any coatings on them or have become oxidized. Think about a brand new penny or a newly polished piece of silver jewelry, a gold ring. These are all very shiny in appearance. Metals also tend to be very workable elements, and by workable, what we mean is we're able to shape these into the shapes, structure, sizes to fit our needs in terms of manufacturing things. You maybe have heard the terms malleable and ductile. Malleable means you can pound metals into very, very thin sheets, which is useful for many, many different things. In fact, some metals like gold, you can pound into such a thin sheet, you can actually see through that sheet of metal. There's also ductile or ductility. That means being able to pull things into thin, long wires, which we know that many circuits and that use metals in terms of being able to form wires out of. It's no surprise, metals tend to be good conductors of both heat and electricity. We use metals all the time in electricity. They also are good conductors of heat as well. You'll notice that metals tend to get hot very quickly and cool down very quickly. If you think about your seatbelt buckle in your car after it's been parked in the sun, it heats up very, very quickly. Meanwhile, metals also chill very, very quickly. They heat up quickly, they get cold quickly. These have all been the physical properties we associate with metals. There's one key chemical property we want to talk about, and that's how they deal with electrons. Electrons are the currency in chemistry. And what metals tend to do with electrons is metals will tend to lose electrons. And being electrons are negatively charged, as you're losing electrons, you're going to form positively charged ions. So if you compare the metals with the nonmetals, they didn't get very clever with the name, literally not metals. You want to think about almost the exact opposite properties. Nonmetals tend to form on the upper right-hand part on the periodic table. These have solids, liquids, and gases as part of it. They tend to be dull in appearance. Certainly the gases are very dull in appearance. They're not shiny, but even the solids are not very shiny like you normally see in the metals. They're also not nearly as workable as metals are. Certainly it's tough to build something out of a gas. It doesn't have any kind of shape or structure or form. But even the solids of these elements tend to kind of be very powdery, very grainy material that it would be tough to actually manufacture something in with a designed shape or size. These tend to be poor conductors of heat and electricity. Just like all the other opposites that they've done compared to the metals, these nonmetals will gain electrons. As a nonmetal is going to gain electrons, electrons being negatively charged, you're going to form negatively charged ions. Your metalloids, these are the elements located between the metals and the nonmetals on the periodic table. They have some of the properties of both. We're not going to relist the properties. It's kind of that in-between land. And I would say one of the big mistakes people do when they're looking at the type of elements on the periodic table is they want to treat it as a on-off switch, like an on-off light switch, on or off, metal or non-metal. You're either 100% metal, 100% non-metal. Well, in reality, there's a nice gradual continuum between metals and nonmetals. And kind of a better analogy that you want to think about if we're keeping this light switch idea is think about a dimmer switch. If you have a dimmer switch on your light, you can still have it fully off, you can have it fully on, but you can also have it anywhere between those two extremes. The exact same thing is happening on the periodic table. You can be very, very metallic on one end, very, very non-metallic on the other end, but then there's a continuum between those two extremes. There's another organization that happens on the periodic table that's a little bit more specific than what we saw for metals, metalloids, and nonmetals. And this gets a little bit into the actual shape that you're seeing on the periodic table. The elements on the periodic table are also organized by periods and groups. The horizontal rows are called the periods, and we just count down period 1, period 2, period 3, period 4. Those are our horizontal rows. You also have the vertical columns we call groups. And what you see for the groups, there's two different numbering systems. The one on the top just kind of goes 1 through 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, just numbering across, 12, 13, 14, 15, 16, 17. Then there's also another numbering system that gets used for the groups, and you see this on this periodic table. And this one's a little bit of an older numbering system, but it still gets used because it displays some very important facts. And we're actually going to use the older numbering system because it does a better job explaining some things. It's the A and the B system. 1A, 2A. Across the middle are all the B's that we're kind of lumping together right now. 3A, 4A, 5A, 6A, 7A, 8A. So we're going to be using the older system that uses the A's and the B's, and we'll see why later on in the course. Using the older system gives you direct information right away that you're going to find useful without having to do anything else. That's why almost everyone still uses the older system as opposed to the new system. So as we talked about as we were looking at it, periods are the horizontal rows on the periodic table. Groups are the vertical columns on the periodic table. What you may sometimes hear is the older term for groups. Sometimes they're still called families. And that's going to be a very important kind of way of thinking about it. We said the groups are numbered two ways, the older system with the A's and the B's, and the newer system with the 1 through 18 just going right across. We're going to be using the older system because that provides us some useful information for some other things that we need to do with some of the elements. The real reason that you see things organized on the periodic table the way you do is the elements in the same group have similar chemical properties. That doesn't mean they'll be identical, but that means two things in the same group are going to be far more similar than they are different. Even if when you look at a periodic table, you see that oxygen and sulfur are in the same group and you think, man, oxygen and sulfur are really different. Oxygen's a gas, we need it for life, that's what kind of powers and fuels our metabolism. Meanwhile, sulfur is this powdery, kind of yellow, smelly solid that can't be used to power our metabolism. We're focusing on the difference because the differences are important, especially in terms of life and how we know it. But when you look at everything oxygen and sulfur does, despite those differences we just listed, they are far more similar than they are different, even though those differences are important. So that's why the periodic table is not a perfect square or a perfect rectangle. It's arranged such that you can show these relationships between the elements in these vertical groups. Now we're going to go through some of the groups. Some of the groups have common names that we need to be familiar with. Not all of them, but some of them that are used so readily we just have to know what that means when that group name is used. And we're also going to talk about a key chemical feature for a lot of these groups. So we're going to look at the group names and the properties. So group 1A, the first group that we're looking at, that's hydrogen's group: hydrogen, lithium, sodium, potassium, rubidium, cesium. That group does have a common name we need to be familiar with. Those are the alkali metals. And their common chemical feature that we're going to use this chapter and talk about later is what type of ions they form. And things in group 1A will form +1 ions. Next group over, group 2A, that's beryllium's group: beryllium, magnesium, calcium, strontium, barium. Those are the alkaline earth metals. That's a common name that gets used to describe them. And they end up forming +2 ions. The next set of elements I'm going to kind of group all together. These are all the B's. This is that whole middle portion of the periodic table. We're going to loop those all together right now and call them the transition metals. Okay? We often don't think about the actual individual groups and kind of put them all together. The reason why we're putting them all together is that's kind of the oddball section of the periodic table. We recognize a lot of common elements in there: copper, nickel, iron, very common metals that we use all the time. But what kind of makes this an oddball group is they can form positive ions of various different charges. They're not set on doing necessarily one thing. They won't just form one type of ion, they'll form lots of different ions. And sometimes even an individual element will form different ions. Something like copper generally forms +1 and +2 ions. Iron forms +2 and +3. Something like titanium likes to be +2 and +4. Manganese can go anywhere from +1 to +7. So being they can kind of do multiple different things, we're keeping those together in one big group right now. Next group we're looking at is group 3A. This is boron's group: boron, aluminum, gallium. There's no commonly used name that's used for this group, so we don't have to worry about that. The common chemical feature you want to think of is forming these +3 ions. Next group is group 4A. This is carbon's group: carbon, silicon, germanium. Group 4A, again, no common name that's used, so we don't have to worry about remembering what a common name is for that group. Usually you do not see a lot of ions coming from that specific group. Farther down in the group, when you get down to tin and lead, you might see some positive ions being formed there, but generally you don't find a lot of ions in that group. Group 5A, nitrogen's group, nitrogen, phosphorus, arsenic, that group. Group 5A, no common name that gets used for that group. But here we're really starting to get into the nonmetals, and these are really going to form negative ions, and the negative ions they end up forming are -3 ions. We move over to group 6A, oxygen's group, oxygen, sulfur, selenium, that group. No commonly used name we need to associate with that group, but this group will usually form -2 ions. That's their common chemical feature. As we're moving over to group 7A, fluorine, chlorine, bromine, iodine, this now does have a common name that we need to be familiar with. These are the halogens, and these halogens will usually form -1 ions. Last group on the periodic table is group 8A. This does have a common name we want to be able to associate with and be familiar with. These are the noble gases, and these will not form any ions. Noble kind of being that old English term for inert, unreactive. We're not expecting a lot of ions coming from this group. Kind of looking at the periodic table again, you can see the charges. If I quickly go through the charges again, group 1A, hydrogen's group, hydrogen, lithium, sodium, +1. Next group, group 2A, we're looking at +2. Everything here in the middle, and that can actually include a little bit over here as well. These are transition metals. These are going to be plus something, but we're not sure what it is yet. Group 3A, we're generally looking at +3 ions for the most part. Group 4A, no real ions till we get down to things like tin and lead. Group 5A, now we're kind of more into our nonmetals, so we're looking at -3 ions. Group 6A, oxygen's group, those are those -2 ions. Group 7A, the halogens, those are -1 ions. And group 8A are noble gases, no real ions that we have to deal with here. So the second part of this presentation is on chemical nomenclature. And what nomenclature is nomenclature is a systematic way of writing names and formulas for compounds. There's a huge number of different compounds that exist. The job of nomenclature is to have a system to clearly communicate that chemical information, such that everyone's on the same page and you can effectively communicate. Everyone's speaking the same language. We're using terms appropriately. We're having some standard conventions to be able to clearly, not just in verbal communication, but also in writing, express exactly what we mean, such that whatever the writer is writing, the reader is seeing it the exact same way. So in this course, we're going to learn the basic rules for writing formulas and names for some of our simplest chemical compounds. Now there's two types of compounds we're going to name, so we want to make sure we're able to differentiate these from each other. The first type are ionic compounds. Ionic compounds are formed from the attraction between a positive ion and a negative ion. So if you think, well, what type of elements are going to give me the positive ion? Well, metals are going to give you those positive ions. What type of element is going to give me these negative ions? Well, the nonmetals are going to provide those negative ions. So generally when you see a metal combined with a nonmetal, you should be thinking ionic compound. There's another type of compound that we want to talk about, and these are covalent or molecular compounds. These are very different in that we have absolutely no ions. There are no ions that happen here. Generally, these covalent compounds are formed from the sharing of the electrons. The sharing of the electrons, well, this isn't going to be metal and nonmetal anymore. We think about our covalent compounds from coming from two nonmetals. Here we want to go over the rules for naming ionic compounds. And there's 4 steps or 4 rules that we want to follow. The first rule is that we name the positive ion first, and we keep the name of the element. Second rule is we name the negative ion second. We chop off the ending of that element and replace it with the IDE ending. The next rule is only going to apply for transition metal ions only. And for transition metal ions only, we use a Roman numeral to indicate the charge that the transition metal ion has. The fourth rule is if there's more than one of the polyatomic ions present, we use parentheses around the polyatomic ion and place that subscript outside those parentheses. Now, the best way to get good at nomenclature is to see and then do just a whole bunch of examples. So in a separate video, we'll have a video just on nomenclature examples that illustrate and use these rules. What would be a good idea is before you watch that nomenclature video to print out this slide such that you're able to look at these steps and rules before we actually start going through the examples in that video. As we said, we had another type of compound. We had ionic compounds. We also have covalent or molecular compounds. They have a little bit separate rule list. First rule, name the first element present. Keep the name. Second rule, name the second element. Replace that ending with the IDE ending. Third rule is an always rule, is always use a prefix to describe how many of the second element is present. The fourth rule is a sometimes rule. If, and it's a big if there is more than one of the first element, we end up using a prefix to describe that number, how many there are of that first element. Now, just like for the ionic compounds, the best way to get really good at doing nomenclature is to see a bunch of examples and then work through a bunch of examples on your own. So we're going to have a separate video on nomenclature with some examples on how to go through these steps or these rules. You want to make sure you watch that separate video. What would also be a good idea is before you watch that video, print out the slide. That way, as we're going through the examples, you'll have these 4 rules, these 4 steps that you can kind of be following along with as we're going through and working through these nomenclature examples. So definitely make sure you watch that separate nomenclature video.